Hello, everyone. Good to see so many of you today attending our talk. We are very excited to be here at Black Hat and to present our research on how we attacked the boot chain of some Samsung devices from the Galaxy A family. So today we will show you a chain of bugs that allow us to take control over the device through the USB ports and ultimately to leak secrets that are stored in the secure vault on the device. And this research started last year at Quark's lab. And so, yeah, today on stage you have Raphael and myself, Maxime, but we want also to thank our colleagues Damiano and Gabrielle who helped us on this project. So last year at Recon, we presented this research. We asked ourselves how Android protects the user data through its encryption scheme. And for that, we bought a device called the one you see here, Samsung Galaxy A22. And this device is known to have a boot RAM vulnerability that can be exploited with an open source tool called NTK client. So using this tool, we were able to bypass the first stage of the secure boot. And from there, we patched the rest of the system so that we could extract all the ingredients required to brute force the credentials of the user. So this is the device I'm talking about. As you can see, it's a rather cheap device. And it is based on a Mediatek system on chip. So it runs Android, but you will also find a mix of closed source components from Mediatek and Samsung. For example, the Trazon OS here is Tigris, which is designed by Samsung. And as I said, we have this boot RAM vulnerability that we can exploit using NTK clients, and it was quite nice to have it in order to debug the exploits that we will present today. So we focused on this device because we had it. So all the bugs we will present today works on this device, but they also apply to other devices from the same family of device, even some of them for which the vulnerability in the boot RAM has been fixed. So before we get to the actual bugs, we need a bit of background on how the secure boot works on Mediatek system on chips. So when the CPU starts, it will run a read-only piece of code that is called the boot RAM, and it will run with the highest privileges in the secure world with the EL3 privilege level. Then the boot RAM will start a second stage bootloader called the preloader, and the preloader will then start the ARM-trusted firmware that is also called the secure monitor. And it is the piece of software that will run with the highest privileges on the device once it's fully booted. The preloader will then start the Trazon environment, which is Tigris, and finally, a third stage bootloader called Little Kernel. Here we call it LK. So this bootloader is in charge of booting Android, and it's actually the component we will look into right now. So Little Kernel is open source originally, and it's very common in the Android ecosystem as a bootloader. And as I said, it will start Android, and for that, it will verify the Android images using a feature called Android Verified Boot, which is the standard that you will find implemented in a similar way in other devices. Now, the Little Kernel bootloader we have here is a closed source version that was modified by Samsung. They added a couple of features, such as Odin, which is a recovery protocol that allows to flash partitions through USB. We also have the NOC security bit. It's a way to void the warranty of the device when the bootloader is unlocked. So it's security for Samsung rather than for the actual user. And yeah, you have a bunch of little features like this. And one that was particularly interesting for us is a JPEG parser that is used to show logos on screen of the device and error messages as the one you see here. And it raised our interest because these JPEGs are placed into a tar archive that you will find in the upper ARM partition. And this archive is signed, but is never checked at boot. So anyone capable of modifying the internal memory of the device can actually change these JPEGs. And as we all know, parsing JPEGs can be a difficult task. Here we are citing Logo Fail, research by Bannerly. They presented it last year. And they basically found many vulnerabilities impacting various image parsers and in many boot chains. So it's a good reminder of that. So to target this JPEG loader, we first need to understand how it is loaded in Little Kernel. And this is the code responsible for that. So the first part of the code actually allocates a constant size buffer on the heap. Then we have a function that we call the read JPEG file. It's the name we gave, but you get the idea. This function takes a file name as a first argument. It will look in the tar archive using this file name, and it will read the JPEG and place the content in the buffer we previously allocated. And finally, we have this pimage function that will pass and render the JPEG on screen. Now, some of you might wonder why do we have a 0 as a third argument, this function. And the third argument here is supposed to be a maximum size. So when the system, before it reads the file, it will look in the tar header for the size of the file, and it will compare it to the size provided. So if it's bigger, it will trigger an error, and it will stop reading the file, unless the size provided is 0, which in this case, the test is ignored, and the file is read anyway. So we have a first vulnerability, a heap overflow here. It was rather quick. And the question we ask ourselves now is it exploitable? So to answer that question, we need to understand a bit how the heap algorithm works. In this case, it is called mini heap, and it relies on a doubly linked list. You have 3 chunks that's all members of this list. They are all placed in the same memory pool, and they all start with the same header as that you see on the right. So you have a first pointer pointing to the next, so the previous chunk, followed by another pointer pointing to the next chunk, followed by the size, and followed by the actual content of the chunk. So if an overflow happens, we may overwrite the metadata of the header of the next chunk. And there is a way to turn an overflow into an arbitrary write. And this is because how the allocation algorithm works. So after an allocation, a chunk is removed from the free list. And to do so, the system will dereference the next and pref pointers of the chunk being allocated in order to access the next and previous chunks, and in turn modify the next and pref pointers so that they point to each other and not to the chunk being allocated. So long story short, if we control the header of a chunk that is being allocated, we have a write-what-where primitive with the only constraint that both values must be writable addresses. Now, a few words about the mitigations in Little Kernel. As you can see, there are not many, none, we can say. No ASLR, no canaries, and more importantly, the heap is executable, which makes the exploit strategy rather simple. We use a primitive to overwrite a pointer that the code will jump to. In this case, it's the return address in the stack. And we will make it point to a shellcode that we place in our JPEG buffer. So here is a representation of the free list. And in purple, you see the JPEG buffer that was just allocated. So the system will read the file, and it will fill the buffer with it until it overflows and overwrites the next free chunk. And we will replace this next free chunk with a fake chunk where the next pointer points to the return address in the stack, and the pref pointer points to the shellcode inside our JPEG buffer. And so that when the next allocation happens, the system will dereference the next pointer of the fake chunk and will replace the return address with the one of the shellcode, so the one that was present in the prev pointer. And when the function returns, we have our shellcode being executed. So we have a first vulnerability here that leads to a code execution in Little Kernel. It's persistent. It will survive both reboots and factory reset, and this is because the partition containing the JPEGs is never wiped, even when you factory reset the device. So we have code execution in Little Kernel, but since Little Kernel loads Android, and with a little bit of work and patching the system, the firmware, the code of the Little Kernel, we can take control over Android. So basically, we control the full normal world, both EL1 and EL0. Regarding the impacts, all the Samsung devices based on Mediatek system on chips, or at least all of those we looked into, are vulnerable, and which includes the ones where the boot RAM vulnerability I presented at the beginning has been fixed. So that's nice. We have a code execution in Little Kernel, but now we need a way to flash the malicious JPEGs on the flash memory without being already privileged. And that is the question we will try to answer now. And for that, we will take a look at Odin, the recovery protocol that is implemented by Samsung that allows to flash partition through USB. And it's also implemented in Little Kernel. And we have two clients that are available. One that is the official one, not super practical and closed source. And there is an open source client called AMDL that we actually use in our proof of concept. So internally, Odin, before flashing an image, it will authenticate it. So you need to have a signature as a footer in every images. You have an example of a signature here. And for that, it will rely on two internal structures, the first one being the partition information table that we will call the PIT, and the second one being a global structure, a global array that indicates how the partitions should be authenticated. And the PIT is actually stored in a fixed address in the eMMC. It indicates it gives information about the partitions. You have an example of entry on the right, so you have a couple of fields such as the block counts, the name of the partition, and so on. And it's interesting to note that a partition not present in the PIT cannot be flashed through Odin. The PIT can be updated, though, but it requires a signed image. Now, regarding the authentication, we have this global array that indicates how an image should be authenticated. And in this case, if an image is not present in this array, it will not be authenticated. So if we compare the PIT and this global array, we get a list of partitions that can be flashed without authentication. And this is the list you see here. The first thing we can say is that a param is not part of the images we can flash because it is actually authenticated. But there are other interesting partitions that we can play with. And it's the case of PGPT and SGPT. They both point to the header of the GPT, so the GUID partition table. And this GPT is similar to the PIT in a sense that it describes the partition. So we have quite an interesting primitive here. Without authentication through the USB cable, we can reshape the partition table of this device. Now, a few words about GPT and PITs, because they are doing more or less the same things. Why do we need these two structures? So the PIT is actually used for Samsung features such as Odin and such as the JPEG loading. So the upparam partition containing the JPEGs is actually retrieved from the PIT, using the PIT. So we can't simply mess with it through the GPT table. And the GPT table, on the other hand, is used the rest of the time. For example, when loading the Android images. So we have a nice primitive, but what can we do with it? And first, let's take a look at how the PIT is loaded. So this piece of code is running when the bootloader starts. And as I said already, the system will try to retrieve the PIT when it starts from a default address. But we also have this routine that is quite interesting. The system will look for a partition called PIT in a partition table, and if it exists, it will load it from there. And what is good for us is that these two functions relies on the GPT table, and we can change the GPT table. So basically, we can add an entry called PIT, and the system should load the PIT not from the original location, but from the new one. So we came up with the following strategy. Here you have a representation of the flash memory, and you have the GPT and the PIT pointing to more or less the same partitions. And the first partition here is called MD5 HDR. I'm not sure if you recall, but it's one of those we can flash without authentication. So we will replace it with a new upparam partition that contains the malicious JPEGs. The next partition is called VB-MetaVendor. It's also one that we can flash without authentication. And here we will replace it with a new PIT that is a copy of the original one. Sorry. Except that we will rename FD5 HDR into upparam, and we do the other way around with upparam. And the final step is that we modify the GPT table, and we will rename the PIT, the VB-MetaVendor partition into PIT, such that at next boot, the new PIT is taken into account and not the original one. And when the system is asked to load a JPEG, it will load it from the new upparam partition. And it actually works. As you see here, we see on the screen Dodge showing up. It means the exploit worked. So yeah, so we have a second vulnerability that is a authentication bypass. It's Odin that allows us to, from the USB, to flash anything on the eMMC, including the JPEGs in the upparam partition. And similarly to the previous one, this vulnerability impacts Samsung devices based on Mediatek system on chips. So we have a little demo. Let's try it. So we have here a device that is a Samsung A22.5F. And what I want to show you first is that I'm connecting through ADB to the device, and the SU binary is not there. That's the expected behavior for a standard Android device. All right. So what I'm going to do now is that I will shut down the device. Here I'm unlocking the interface, but it can be shut down by pressing all the buttons all together for a couple of seconds. So then I'm booting the device in the Odin mode. And once it's done, we are ready to launch the exploit. So basically, we are going to flash the partitions as I explained. There is a little trick happening right now. The device is rebooting again in the download mode, and it's because we want to take control over Android. So we are flashing another partition, the boot partition, that we modified with Magist to get root privileges. So the image quality is a bit poor, but I'm not sure if you can recognize the dodge that is showing up on screen. So it's a good sign. It means that probably the exploit worked. Now we have to wait for the device to boot to get the proof, and that's one of the things Samsung can improve on this device is the boot time. Okay. So normally Raphael is gonna tell a joke. Okay, so the device seems to have booted, and I'm connected to ADB. Can we see? Yes. Let's try SU. Oh, it works. We are root. Okay. So, yes. Okay. So to conclude on the first part of this presentation, we have shown a chain of 2 bugs that leads to code execution in Little Kernel. It is persistent, and yeah, it impacts many Samsung devices based on Mediatek system on chips. And we can trigger this vulnerability through USB. And it will give full control over the normal world. So we have full control over Android. We are root. We can already do many things. We can read the messages, look at the pictures, and so on. But there are some secrets that are protected by Android, by design. They are stored in the secure world, and we still don't have access to these secrets. So I'm going to let Raphael tell you how to retrieve the secrets that are still hidden from us.
Thank you, Max. All right, so now that we have full control over the normal world, with both Little Kernel and Android being compromised, we are ready to step into the secure world. And our next target to do that will be the Arm Trusted Firmware, or ATF. So what is ATF? ATF is the secure monitor used to reach the secure world from the normal world. So as you can see on this picture, it stands right in the middle. When you are in, let's say, a regular Android application and that you want to use the secure world to perform maybe crypto operations, you ask for ATF to transfer your request to the secure world. And to do that, we use a special ARM instruction called SMC, which stands for Secure Monitor Call. And what this instruction does is that it triggers an exception handled by the EL3 monitor, which is ATF in our case. Then the monitor decides what to do based on the ID of the SMC and also the parameters that are passed through the registers. So why do vulnerability research on ATF? Well, as you have seen before, it runs in EL3, which is the highest privilege level on the device. So finding a bug here can definitely be devastating. We can reach it from normal world through the SMCs. We need to have kernel access, but we were roots on the device, so that's not a problem. The code is fairly simple, so reversing is going to be simple, yes. However, it interacts a lot with hardware through unknown registers, so maybe doing fuzzing might not be the right idea, as we won't be able to properly emulate these behaviors. So we will just focus on static analysis for now. So the first step is extracting ATF. So inside a regular Android ROM image, you have several partitions, and one of them is named teeverified.img. It contains a lot of interesting things, such as the Tigris kernel, but also the ATF, which is what we want. So if we open this file using an hex editor, this is what we get. So the way this file is structured, it has several entries, and each entry has its own header. So at offset 0, you have the first header of the first entry. In red, you have a magic byte. In green, you have the size of the entry. And in blue, you have the name of the entry. And as you can see, the first entry at offset 0 is ATF. So we are lucky. We won't have to search for it. The header is 0x200 byte long, so we just skip to this offset. And highlighted in purple, you can see the magic string MTKTE, but in reverse. This is the start of ATF. So we have the offset, and we have the size. We can extract it and load it into our favorite disassembler, or in this case, the compiler, and look for the different SMC handlers. So here we have two handlers, one for the secure world and one for the normal world, the second one. This is what we're gonna dive into. As you can see, here are the arguments of the SMC. They directly come from the normal world, so we control them. The first one is the SMC ID, and then the rest is depending on the SMC. One interesting SMC that we found was this one. As you can see, it uses a global array, which is initialized to a hard-coded memory address. And then we retrieve in the out value variable a value from this global array using the first argument that we control, because it comes from the normal world. The problem here is that we never check this argument. So it can be whatever index that we want. So basically, this is an out-of-bound read bug. And we are able to read any address that we want in ATF. So we are able to leak 4 bytes from the ATF virtual address space, which means that we can dump all ATF data. But we can't leak anything from other software components, such as Tigris, for example, or trusted applications. So at this point, it could be really great if we could nmap any address we want, right? So let's search for a mean to do that. A second SMC that we found interesting is this one. It calls a function that we named SPM actions. We don't really know what it does, but as you can see, eventually, we reach an mmap function. So this looks interesting, right? We could maybe use it to map a memory range from the secure world. So to reach this function, we need to set the command ID to 1, which is not difficult. We need to have a size less than 1 megabytes. We can do that. And the last parameter is the address. And once again, we have no checks whatsoever on this parameter. So this means that we are able to nmap any address that we want. And if we further dive in the nmap wrap function, we discover that it is actually a physical address. So thanks to this bug, we are now able to map any physical address into the ATF virtual address space. And if we combine this to our bug, the leak bug, we are able to leak anything from the secure world, including the Tigris kernel, including trusted applications. The only limit to this is that we are limited to 8 consecutive nmaps. If we do, let's say 9, the device crashes. So this means that because one nmap is 1 megabyte of memory, we are able to leak up to 8 megabytes of data. But we will see that it's more than enough for what we are going to do. So the important question here is, can we use this vulnerability to leak Keystore keys, for example? First, we need to understand what is the Android Keystore system. This system is used for key storage and provide crypto services to the normal world. The keys are stored as encrypted key blobs inside the Android file system. So Android has no means to process the raw key material. Only the secure world is able to decrypt this. There are 3 protection levels, and the one that is interesting for us is the TEE one, which is also the default one. And yeah, raw key material should never leave the protected environment provided by the trust zone. So those are the different steps that are performed under the hood. First, from the normal world, we send a begin operation request, including our key blob. Then, in the secure world, here it's the keymaster trusted application in charge. It will be able to decrypt this key blob and extract the raw key into secure memory. And then we are able to send several update operations. So let's say, for example, choose the algorithm, the different options, and so on. Here, we need the key to be in memory. So this is very important because if we are to use our bugs, we need to use them only after the begin operation to be sure that the key is still in memory. After that, the trusted application returns the output, and then the key is flushed from memory. So our proof of concept will be simple. We will import a key into the Android key store. Then we will encrypt something using that key. Then we stop the execution after the begin operation is called and the key is in secure memory. And we use our bugs, our two bugs, to leak the right region of memory. Then, because we will have a 8 megabytes dump of data, we try all possible keys to decrypt the ciphertext. So here is a little demo. So to do this demo, we are going to use a tool called Frida. Frida will allow us to hook functions into the normal world to halt the execution. And when the execution is stopped after the begin operation, we will have a script that will trigger our bugs to leak the secure world memory. And hopefully, the key will be in our dump of data. We also watch for the logcat logs because our demo applications will send us the encrypted ciphertext inside it. All right, so we will send the Quarks Lab string to be encrypted into the secure world. As you can see, our script on the left is dumping the secure world memory because the begin operation function has been triggered in Frida. So this can take a bit of time because we are only able to leak 4 bytes of data. So basically what we're doing here is we are dumping 4 bytes at a time by sending multiple SMC. All right. So as you can see in the log, we have our ciphertext, which is the Quarks Lab string encrypted. And we have the dump of data in the file named leakkey1. So now we are going to be able to try every possible key inside the leakkey1 file dump. And hopefully, we will find the key that is able to decipher our encrypted text. So of course, we could have packed every steps into one application or one script, but for the purpose of this demo, it is better to do the different steps to be able to see how it works. So we will try to find the key now. It can take a bit of time. And we found the key. So here, for demonstration purposes, we imported the key only made of A's, but if we generated a key, it would have worked also.
Thank you. All right. So what's next? Actually, it could be the end of this presentation, and it was the end of what we presented at OffensiveCon a couple of months ago. But we received interesting questions, and one of them was, what about the key attestation? So the key attestation in Android relies on the Android key store, and it proves that a key pair is stored in the secure hardware, either the trust zone or a security chip. And along with that proof comes a bunch of information regarding the device, such as the status of the bootloader, is it locked or not? The status of the boot state, is it verified correctly? You have a bunch of IDs, such as the EMEI and so on. And this key attestation is used by SafetyNet and other frameworks that are similar to SafetyNet. So SafetyNet is the one made by Google, and it's used to tell if a device has been compromised. For example, if you have a bank application, the developers of this application may not want it to run on a rooted device because it can be debugged, instrumented, or whatever. So they may use this mechanism for detecting if the environment is compromised and decide not to run if it's the case. So we didn't know much about the key attestation, and for the sake of this research, we took an open source application that will generate the attestation on the device and will pass the results to make sure it's done correctly. And the first thing we noticed is that everything seems fine. The exploit seems not to be detected. So we tried again with another app that is also open source and can be found on GitHub. This time it relies on SafetyNet. And here what we see is that it fails. Basically, it detects that the environment is compromised. So SafetyNet is a research topic on its own. There are too many things to say regarding SafetyNet, so it's not something we will cover today. But it is known that it has heuristics to detect some famous routing frameworks, such as Magisk, which we used in our exploit. So it's maybe the things that were detected here, but it's still unclear precisely what was detected. So if we come back to the key attestation, under the hood, it relies on a certificate chain. And at the bottom, you see there is a root certificate that is self-signed. And this, the private key corresponding to this root certificate is owned by Google. And the other certificates part of this chain have their private key stored on the device inside the key store. Now we have the first key here is the GAK for Google Authenticated Key, and it's actually the same across many different devices, at least all the Samsung A225F. We looked in 2 devices, but we believe that it's going to be the same across all these devices. So they're sharing the same key, basically. Then in orange, you have the Android Keystore Key, which is unique per device, and finally the application key that is generated along with the attestation. And as I said, you have a bunch of information that comes with this attestation that they are basically unique per device. I mean, they represent the device. For example, you have the version of the OS, and you have a couple of fields. I'm not sure you can read from here, but you have the hash of the boot partition. This might be one of the things SafetyNet detected because we modified the boot partition, so the hash may have changed. So the one thing that could be nice is to be able to generate attestations, but decide, I mean, from the attacker point of view, but decide what to put inside these fields. And if we were able to leak one of the private keys involved in this certificate chain, we might be able to generate valid attestations and decide what to put inside. And the key that makes most sense for that is the GAK, because it is the same key shared across different devices. So if you leak it once, you can produce valid attestations for many different devices. So we looked into this key, and we discovered that it is stored in the Android file system in the eKey format. So it's basically the standard format for keys that are stored in the key store. And it's the same format as any other keys, and same as the keys that we leaked with the proof of concept that Raphael showed you. So we came up with a strategy that is more or less the same as the previous one. The idea is to forge a valid begin request with this key. Then we send it to the secure world, we stop the execution, and from there we use the vulnerabilities to leak the memory. And finally, from the dump, we try all the possible private keys. And this time, we don't use encryption or signature. We try to generate the public key out of it, simply because it's faster, it's a multiplication. But this is a theory, and it's still work in progress, sadly, because we are still stuck in step 1. It requires more reverse engineering at the moment to better understand how to forge this begin request that is at least a begin request that is valid. So it's not a failure, it's the unfinished business, right? All right, so that was the last thing we wanted to share with you regarding this presentation. So now a few takeaways. So we presented a chain of 4 vulnerabilities that led to authentication bypass in Odin. Thanks to that, we can, from the USB cable, trigger another vulnerability, a code execution in Little Kernel with persistency. And we have shown that using the other vulnerabilities, we can leak the memory from the secure world, which include the Keystore keys. And yes, it's still unclear if we can leak the attestation keys at the moment. Now, regarding the impact, all the Samsung devices based on Mediatek SOCs seems to be vulnerable, so mainly low and middle-hand devices. And we have seen the vulnerability are quite simple. They could have been easily spotted through code reviews and maybe fuzzing for some of them. But yet they are very impactful. And this is also probably because of the lack of mitigation in Little Kernel and ATF. So we reported all these vulnerabilities to Samsung, and they are all fixed today. And we would like to thank Samsung security team for how they handled the reports we sent. And they made it so they worked quickly so that we could disclose the vulnerabilities in conferences such as this one. So thanks to them. And thanks to you for listening to our presentation. And I'm not sure we have 2 minutes for questions, so if you have some, please step forward. Yeah, there should be a microphone. Just over there, yeah.
Can you hear me? Yeah.
Hi, yes.
Yeah, thanks for your presentation. I saw the conclusion is only affect the low and middle level of the phone. How about the premium ones?
Well, these bugs only applies to phones based on Mediatek system on chip, so I'm not sure they are premium phones based on this system on chips. So maybe that's a topic for another research. I would be happy to show more bugs on premium phones next time, maybe.
Okay, so due to this only happen to the Mediatek SoC, right? The problem.
Yeah, yeah.
And they also fixed the problem.
And they're all fixed, yeah. You should update the firmware.
Thanks.
Yeah. Thank you.
Hi all, thanks for the presentation, was a blast. Does Mediatek planning on releasing like mitigations? You said like there weren't any mitigation active, and so will they install any mitigations at all on all of those?
Sorry, I didn't get it. Maybe can you step a bit? Can you speak closer to the mic? Yeah.
Okay. Can you hear me now?
Yeah.
Okay.
Yeah.
Are Mediatek planning on releasing mitigations like ACLR, all kind of stuff? That's something they will do in the future?
So it's hard to speak in their names. I think that's something I would expect maybe, but I don't know for this device. I think it's already implemented in some high-end devices, for example. So yeah. Okay, well, I think that's it. Thank you, everyone.